some time to get adjusted with this. Yeah. Why do this idea of electric dipole arises? Means, what is the necessity of electric dipole? That one. So if you see the atomic structure, especially, so if you take any substance, some non-conducting substance. So inside the substance, what we get an atom. So the positive ion, the positive and negative charge of atom we can represent by a quantity called as a physical quantity called as a dipole. It's a very much needed to study. I think you might have come across in chemistry, the dipole moment. Okay, this one. If you take any insulator, especially, if you take an insulator, so what we see is like the particular substance will happen. The atom itself will get polarized. So here, if you look at the nucleus will be the charge Zc. The whole charge, the negative charge, the revolving negative charge, we can place it at some point. This will be the nucleus, and the whole, the positive charge, the negative charge, the revolving negative charge will be aligned at one position. So now this is an atom. So this atom, now what I can do is like I can make it as, I can say that it is like a dipole. So from what is a dipole like? The positive charge, the nucleus, the positive charge of nucleus and the revolving negative charge will get positioned at one particular point. So I should not say the negative charge will be here. The effective negative charge, we can take it to be here. So this will be the revolving negative charge. So the atom, I can represent it as a dipole. Fine. So that is what these are like a dipoles. And for a given atom, how they will be? They'll be aligned like this here. So they'll be aligned. The dipole moment of individual atoms will get aligned randomly. This is what happens in the insulator. Now, so to study this material, so what I should do? So shall I assume that this insulator made up of dipoles? So if I can study the behavior of dipole, nothing but I'm able to study the behavior of this material. Moreover, I'm interested how do this material will behave when it is immersed in an electric field. In the presence of electric field, how do this material, what will happen to the properties of this material? To study this, so what this material I'm assuming made up of dipoles. What is the in fact a dipole? The net positive charge, the positive charge of nucleus and the revolving negative charge of the atom, we can consider it to be a net negative charge, that one. So there'll be some separation between them. So then there's a positive charge, negative charge, and there's separation. So I can treat now individual atom as a one dipole. So now what will happen to this dipole in the presence of electric field? Yes, I'll study the individual dipole. So if I can study one dipole, nothing but altogether n times of that effect what will be shown on the insulator. This idea. So to study the behavior of a material when it is kept in an electric field, we are taking help of this dipole idea. So therefore, what is the first necessity now? If I can learn the idea of dipole, it'll be very easy for me to study this, the behavior of insulators in an electric field. Getting the idea, this is the our purpose, application part. Okay, let's come for dipole. What will be the charge of altogether atom? Atom is electrically neutral. How much positive charge is present, that much negative charge will be revolving around the atom. So what do we expect this net charge? Should be 0. Fine. And there definitely what happened, this electron and the nucleus will be separated by distance. So I'll go for average. So you can ask questions, sir, what is the distance you're going to take? So those electrons which are revolving in K shell, they'll have some distance. Those which are in L, M, N. So shall I go for average of that? Average distance of all electrons from the nucleus, revolving electrons from the nucleus. That is what the distance between the net negative charge of atom and positive charge of an atom is what I'm going to consider it here. So this dipole we are going to represent in this way, a negative charge and a positive charge. So this will be plus q, this will be minus q, and they'll be separated by distance 2a. What do you expect this distance 2a? For time being, let me write L. What do we expect L? Kilometer, meter, centimeter, millimeter, micrometer, nanometer. So definitely it is of order micrometer. Of nuclear range, better write. Or for our application purpose, nuclear range, or of order molecular range, I'll write it. That's what, no? The average distance of the revolving electrons from the nucleus definitely will be of order molecular range. Fine. So like this L will be very practically, if you compare with the L, means somewhere at a distance x. X will be anything. X can be anything like 10 centimeter, 20 centimeter, 30 centimeter, even 1 meter also. So what do you expect like a L? So L will be very much less than X. So here we'll put a condition. I think this what happens in the numerical, sir. Why you are assuming like this? This distance will be of order molecular range. Okay, now what is our purpose now? Let's study the electric field and electric potential at various points surrounding this dipole. Let me get into the thing. So let me have a dipole. Let me take the distance between dipoles as this one. Okay, let me define one quantity. Dipole, electric dipole moment. The symbol is P bar. The P is it's a vector quantity. So it is defined as P is equal to L into Q. What is the direction of it? The direction of this will be, the dipole moment will be directed from the negative charge, towards positive charge. This will be the electric dipole moment. So what can be unit for this? Shall we go for a coulomb meter? Charge is coulombs, there's a meter. So the unit for electric dipole moment will be coulomb meter, that one. And it will be directed always from negative to positive charge. It's a convention. Okay, no such a dipole is what I'm going to consider. So first, let me go for the field strength at a distance x. So let me take this a point P. So what is the electric field strength at point P? So we know enough of some mathematics, also like a Coulomb's law, all we did know for point charges. We'll apply this. I do. Yeah, this one. Okay, first we'll calculate. I'll come for the calculation. What is the electric field strength at point P1? Due to positive charge, due to negative charge. Due to positive charge, how it will be? E plus. Due to negative charge, it should be E minus. So this should become KQ. The distance X is measured from the center here. Center of the dipole. So therefore, this should become KQ L minus X whole square, KQ L plus X whole square. So this should become KQ. Shall I write directly? So that this will become, or one step, let me go for it. 2Lx minus L square minus X square minus 2Lx, all divided by L square minus X square whole square. Okay, the next part, KQ, this will become 4Lx. Usually what we assumed, X very much less than L very, or say this. This is here. I'm changing symbol. Any doubt? Please unmute and talk to me. No problem. Huh? x plus a whole square, and I'll rewrite it, something. Let me derive fresh. EP1 should be equal to E plus E minus. What should be this? This should be equal to KQ x minus a whole square KQ x plus a whole square. So expansion of this will be KQ by x square plus a square 2xa x square minus a square plus 2xa all divided by
What is minus 2xa?
will be plus 2xa only, no? Okay, no, this will become KQ 4xa, it will become. Now, what is the dipole moment? How we define dipole moment for this diagram? Dipole moment should be equal to the distance between the charges into magnitude of any one charge. So strictly what happened, what did this 2a represents? 2a represents the distance between the charges. Charges should be equivalent opposite. So 2a into q. So therefore the 2a into q, what shall I write? That should be equal to dipole moment. So here I'll rearrange this one. This will be 2a into q will keep outside. Then what will be left over? 2kx by x square minus a square whole square. 2aq, what it will be? It should be equal to dipole moment. So therefore this will become P2kx. Since a will be very much less than this one, so the net effective dipole moment will be 2p k x cube. A very much less than x. Okay, try to see this. So there's the expression for the electric field strength at point P. I'll call this as, we'll give some specific name for them. So we'll call this as axis of dipole. This is called like a bisector. Okay, agree this. So what is the field on the axis of dipole? 2pk x cube, that one. What is also like k equal to what? You can write 4 pi epsilon naught. So I think in the books, what happened, they're given a better formula. It will be like a 2p by 4 pi epsilon naught x cube. Provided a very much less than a, and it will be in all our applications, it will be that one. Well, similarly, I want the field strength at point P2. Roughly, can I use same formula, or shall we derive one more? I want field strength at this point. So you know enough of some electrostatics here. This point P2 is near to negative charge. So how the field should be directed? Definitely the field will be directed towards right only. So anywhere on the axis of dipole, you want to find out the electric field strength. So what is the formula? There's a formula what you can have. There's the expression for magnitude. What about direction? The field will be directed along the axis of dipole. At all points on the axis of dipole, the electric field should be directed along the dipole. And as we move away from dipole, what will happen to field strength? Will decrease. The field strength will decrease. As we move away from the dipole along the axis, the field strength will keep on decrease. Able to get this one? Okay, similarly, I want on the bisector.